This video is going to cover our lecture on chemical bonds and chemical reactions. If you can recall from last week, the number of electrons an atom has on its valence shell, which is the most outer shell, is interconnected to the atom's location on the periodic table. So if we look at this periodic table here, let's say for example, nitrogen. Nitrogen is in group 5A, right? So that means group 5A atoms have 5 electrons on its most outer shell, which is the valence shell. Similarly, if you look at, let's say lithium here. Lithium is in group 1A, right? So all of group 1A atoms have 1 electron on its most outer shell, the valence shell. The lack of chemical reactivity of the noble gases, which is group 8A, found here. This is group 8A, the noble gases. It indicates that high degree of stability of their electron configuration. Helium, right, has a filled valence shell of 2 electrons because we know that the 1s can only get a maximum of 2 electrons, so that is indicated here as 1s2. And then when we look at our next noble gas, which is neon, neon is filled with 8 electrons on its valence shell, so that is shown by the 2s2 and the 2p6. And then moving on to our argon, which is the third here of our noble gases, follows the same rule. It has the 8 electrons in its most outer shell, which is the valence shell, and that is shown by the 3s2 and 3p6, and so forth. So this goes into asking, what is the octet rule? The octet rule is when undergoing a chemical reactions, atoms of group 1A to 7A elements tend to gain, lose, or share electrons to achieve an electron configuration of having 8 valence electrons. So what that means is we know that the noble gas has 8 electrons in its most outer shell. So when we have elements that have less electrons in their valence shell, it's going to want to either gain or lose an electron or even share it to fill that 8 electron space. An atom with almost 8 valence electrons tends to gain the need electrons to have 8 electrons in its valence shell, right? So if we have, let's say, 7 electrons, that means that this atom is going to want to gain 1 more electron to fill that outermost shell of having 8 electrons. And this is known as an atom becoming negatively charged, so it's called an anion. And then similarly, or should I say, on the other hand, we have cations, which is the opposite. If the if the atom is going to lose an electron, let's say we have an atom that has 1 electron on its valence shell, that's going to want to lose that 1 electron so we can have that valence shell of 8 electrons completely filled. So when you lose that electron, it is called a cation, becomes positively charged. It is important to note that when an atom gains or loses electrons to achieve an outer shell of 8 valence electrons, it still remains the same atomic number. So by meaning that is that the number of protons and neutrons in the nucleus stays the same. So let me do an example here so you can understand. We have Cl- versus Ar, right? If we look on our periodic table, we have Cl minus, we have Cl here, but our example is saying Cl minus, which means that the Cl has one additional electron. And then we have the Ar here. We know that Ar, the argon, has 8 electrons. The chlorine has 7 electrons, right? Because it's in group 7a. So Cl minus will mean that the chlorine has 8 electrons. So let me write that here. Cl is in group 7a. Ar, Cl, and Ar. So Cl is atomic number 17 and Ar is 18. So this means that Cl has 17 protons, right? And Ar has 18 protons. Then we know Cl also has 17 electrons. Ar has 18 electrons. But when we have our Cl minus, the Cl still remains the 17 protons, but this minus indicates that we have one additional electron, so therefore Cl minus will have 18 electrons. So the electrons are identical to the argon electrons, but the protons remain identical to the Cl. Does that make sense? We have an example here that says, show how the following chemical changes obey the octet rule. So we have a sodium atom loses an electron to form a sodium ion. So we have our sodium atom, right, loses an electron, so that becomes Na+. So when you lose one, it's plus an electron. That is Na is 1s2, 2s2, 2p6, 3s1. So when we lose that electron, that is losing the 3s1. So now we have our valence shell completely filled. So Na plus will be 1s2, 2s2, 2p6. Another example is a chlorine atom gains an electron to form chloride ion. So that's the other way. So we have our chlorine gaining an electron, and we get the chloride ion. And if I show this in the Lewis structure, chlorine has 7 electrons, right? So we have this one lone pair here. This one, let me draw in blue. This electron is going to want its partner, right? So that we add this electron. When we add that electron, we'll have the most outer shell completely filled. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5, right? So if you look here, we have 5 plus 2, that's 7. So we want this to be 8. We want this 5 to equal 6, right? So our Cl minus will be 1s2, 2s2, 2p6, 3s2, 3p6. This will have our most outer valence shell completely filled. A magnesium atom forms a magnesium ion Mg2+. So this here has 2+. So how do we do this? Mg magnesium is 1s2, 2s2, 2p6, 3s2. So we're going to lose the 2 electrons from here, and Mg2+ will be 1s2, 2s2, 2p6, right? We have the 2 electrons that we lost. So this also fills the most outer shell. There are enormous differences between the properties of an atom and those of its ions. Atoms and their ions are completely different chemical species and have completely different chemical and physical properties. Okay, guys, that's very, very important for you to understand. An example of sodium and chlorine. So, for you to understand this statement here, sodium is a soft metal, right, made of sodium atoms. It reacts violently with water. And then we have chlorine atom, which is very unstable, and it's even more reactive than sodium atoms. If we have them each separately, they're very dangerous, right? They're poisonous. But sodium is Na, chlorine is Cl, right? If we have NaCl, which is table salt, literally, you consume it. It's made up of sodium ions and chloride ions, and these two react together and are very stable and unreactive. And they don't react with water, so it doesn't become poisonous anymore. Side note here, because atoms and their ions are very different chemical species, we must be careful to distinguish one from the other. Now I'm going to go over how we name anions and cations. So we use the International Union of Pure and Applied Chemistry, which is the IUPAC. It's called IUPAC. First thing I'm going to go over is naming monatomic cations. A monatomic, right, which means that there's only one atom, cation, forms when a metal loses one or more valence electrons. Elements of group 1a, 2a, and 3a form only one type of cation. For ions of these metals, the name of the cation is the name of the metal followed by the word ion. Right? So like from group 1a, sodium, right? Sodium would become sodium ion. There is no need to specify the charge on these cations because there is only one charge, right? An example here is sodium. Na plus is sodium ion and Ca2 plus is calcium ion. The charges are based on the number of electrons each atom must lose in order to achieve an outer shell of 8 valence electrons, which is the octet rule. So if I write that for you, Na has 1 electron in its most outer shell, so it becomes Na plus because it'll lose this electron right here, right? And then calcium has 2 electrons on its most outer shell, and that will become Ca2+ because it will lose both of these electrons. The magnesium atom will readily lose 2 electrons in order to obtain the same number of electrons as neon. So magnesium has 2 electrons on its outer shell, so it's going to lose these 2 just like the calcium did, and that will be Mg2+. So this table here has the names of cations from some metals that form only one positive ion. So hydrogen, you lose an ion, it becomes hydrogen ion. Lithium is lithium ion, sodium is sodium ion, potassium, potassium ion, and so forth. Most transition and inner transition elements form more than one type of cation, and therefore the names of these cations must show the charge. And this is shown by using Roman numerals. So here is a good example. We have copper, right? So copper plus becomes copper 1 ion. Copper 2+ becomes copper 2 ion, right? The common name here, you see it says the cuprous ion and the cupric ion. That is used in, it's not the IUPAC name though, so the systematic name is the IUPAC name that I went over previously. So you see there's multiple ions that have the 1 and the 2, or this one, iron here has three ions. Tin has 4. So it's very common to have multiple. Oh, here. In the older common system, for naming metal cations with 2 different charges, the suffix OUS is used to show the smaller charge, and the IC-ic is used to show the larger charge. So if we look here, the cuprous ion, the OUS is the smaller, the ic, cupric, is the greater. Naming monatomic anions. So a monatomic anion is named by adding the "ide" to the stem part of the name. The charges are based on the number of electrons needed to be gained by each atom in order to achieve an outer shell of 8 valence electrons, which is the octet rule we went over. So here we have an anion, hydrogen, so that'll become hydride. You add the ide. Fluorine becomes fluoride. Chlorine becomes chloride. Bromine becomes bromide, and so forth. The next section is naming the polyatomic ions. So the polyatomic ion contains more than one atom. An example are like hydroxide ion, right? So you have oxygen and hydrogen, or phosphate ion, you have the phosphate and oxygen. We will not be concerned with how these ions are formed, okay? So we only need to know that they exist and they're present in materials around us. Here is a table that has the polyatomic ions. We know we'll have a lot of examples with ammonium, hydroxide, nitrate, what else? Sulfate. These are all common ones that, phosphate. These are all common ones that you'll see further on. So what are the 2 major types of chemical bonds? We have ionic bonds and covalent bonds. Ionic bonds is a bond between a positive ion and a negative ion, and this is usually formed between a metal and a non-metal. On the other hand, covalent bond is when the electrons on the outer shell of two atoms, the electrons are getting shared by the two atoms. And this is shown between two nonmetals or metalloids and a nonmetal combined. So another way to determine the bond type is to compare the electronegativities of the atoms involved. So what actually is an electronegativity? That is the measure of an atom's attraction for the electrons it shares in a chemical bond with another atom. So if we look here, electronegativity increases as you move to the right and as you move up on the periodic table. So fluorine here has the highest electronegativity of 4.0. Ionization energy versus electronegativity. So ionization energy measures the amount of energy necessary to remove an electron from the atom, right? Electronegativity, on the other hand, measures how tightly an atom holds the electrons that it shares with another atom. Both electronegativity and ionization energy generally increase from left to right and going from bottom to top. So an example here, judging from their relative positions on the periodic table, which element in each pair has the larger electronegativity? We have lithium or carbon. Lithium or carbon, right? Which has a larger electronegativity? Obviously carbon at 2.5. Then we have nitrogen right here. Nitrogen and oxygen, which has the higher electronegativity. Oxygen is 3.5. Next one says carbon or oxygen. Carbon here, 2.5. Oxygen, 3.5. So which one is higher? Oxygen. Oxygen has a higher electronegativity. Forming ionic bonds. An ionic bond forms by the transfer of one or more valence shell electrons from an atom of lower electronegativity to the valence shell of an atom of a higher electronegativity, right? The more electronegative atom gains one or more valence electrons and becomes an anion, and if the atom is less electronegative, then it loses one or more valence electrons and becomes a cation. The compound formed by the electrostatic attraction of positive and negative ions is called an ionic compound. To form an ionic compound, right, the difference between the electronegativities between one atom and another atom needs to be 1.9 or greater. If it's less than 1.9, then it'll be a covalent bond, not an ionic. So let's do an example now. It says here, bond formed between the metal sodium, electronegativity of 0.9, and the nonmetal chlorine, electronegativity of 3.0. Question asks, what is the difference in electronegativity between these two elements? So we take the difference as 3.0 minus 0.9. And that is equal to 2.1, right? 2.1 is greater than 1.9, therefore it is an ionic compound. If we look here, that the single valence electron of the sodium atom is transferred to the chlorine to have that octet rule, the octet rule for both the sodium and the chlorine. So the Na loses this one electron. This one electron will go to the chlorine. So this one electron will go to here, right? And both will have the octet rule completed. So predicting formulas of ionic compounds. The formula of an ionic compound shows the simplest whole number ratio between cations and anions. So we won't have like decimal points. In an ionic compound, the total number of positive charges of the cation and the total number of negative charges of the anion must equal. To predict the formula of an ionic compound, you must know the charges of the ions involved. So let's write the formulas of the ionic compounds formed in these ions. We have here lithium and bromide ion. Lithium ion and bromide ion, right? So lithium, here, lithium ion is Li plus, and the bromide ion here is Br minus. So we have one charge positive, one charge negative. Therefore, we will have LiBr. If we look here at barium ion is Ba2 plus, and we have our iodide ion. Iodide here is I minus. So our charges now, unlike our example before, are not the same. 2 plus and 1 minus are not the same. They cannot cancel each other out. So we have to do the math in order for the 2 plus and the 1 minus to cancel out. And how do we do that? So we multiply the charges. So I'm going to write minus 1 here so you guys understand, even though we don't put the 1 when we're writing one negative charge. So minus 1 multiply with 2, so multiply by 1, and then vice versa. We multiply the minus 1 by 2 to have the charge. So what does this mean? For one barium ion, we need 2 iodide ions for the charges to equal. So we write that as 1 barium, we need 2 iodides. Does that make sense? If we write it this way, our charges cancel out and are neutral. Another example here is aluminum ion and sulfide ion. Aluminum ion, here's aluminum ion, it's Al3 plus, and sulfide ion here is S2 minus. So the charges are not neutral, right? So we have to multiply it. So we multiply the 3 with 2 and the 2 with 3. This way we will have 6 and 6 on each side, and that can cancel out. So we have 2 aluminums, right? We multiply by 2, so we have Al2, and the sulfide we multiply by 3, so that means we have 3 sulfides. This way it all cancels out. Next, I'm going to go over how we name ionic compounds. To name an ionic compound, we give the name of the cation first, followed by the name of the anion. Binary ionic compounds of metals that form only one positive ion. Binary compound contains only 2 elements, because as you can see, binary, so 2. In a binary ionic compound, both of the elements are present as ions. The name of the compound consists of the name of the metal from which the cation, which is a positively charged ion, was formed, and then it's followed by the name of the anion, which is the negatively charged ion. So we generally ignore subscripts in naming binary ionic compounds. Let me do an example for you to understand. Here we have an example that says name these binary ionic compounds. So we have AlCl3. So how do we name that? Al is our aluminum and Cl is the chlorine. So we name this as aluminum chloride. Right? We don't say 3-chloride. We just say aluminum chloride. Our next example is LiBr. So that is lithium and bromine. So that would be lithium bromide. Next we have Ag2S. Ag is silver and S is sulfur. So that would be silver sulfide. You guys see how everything ends in an "ide"? And here again we have the 2. We don't say 2 silver sulfide, we just say silver sulfide. Our last example here is NaBr, which is sodium and bromine. That would be sodium bromide. Again, ending in "ide". Next is vice versa. Write the formulas of these binary ionic compounds. So we have barium hydride. How do we write that? So barium is Ba and hydride is hydrogen, right? So let's check here on the periodic table. I'm going blind, I can't find barium. Ba, look on a bigger table, sorry guys. Oh, right here. Oh wow, barium. So barium is in group 2A, right? So that means that it has 2 electrons on this outer shell. So it would need not sure if that's a good example. Let me do the following example because that's going to confuse you. Barium is BaH2, but if I go into details, you guys are going to get totally confused. So let me just leave it like that. So sodium fluoride, sodium is Na, fluoride is F, and we write that NaF. Calcium oxide, calcium is Ca, oxide is O, so that we would write as CaO. Next, I'm going to go over binary ionic compounds of metals that form more than one positive ion. Many transition metals form more than one positive ion. So for systematic names, we use the Roman numerals in the name to show the charge, and for common names, we use the Ost and Ich system. So, an example. Give each binary ionic compound a systematic name and a common name. So CuO is copper and oxygen. The systematic name for CuO so copper, Cu, and oxygen. Oxygen, if we look on the periodic table, I don't know why I didn't copy and paste one there. So oxygen here is in group 6A, right? So oxygen has 6 electrons on its more outer shell, and then copper is here. So we would have for here, sorry, scrolling down, oxygen would have to gain 2 electrons from the copper, right, to fill that octet rule. So this is 2 plus here. So we would write that the systematic name would be copper, parentheses, 2, in Roman numeral, oxide. And then the common name for this is cupric oxide. Now for Cu2O, for our next example, so oxygen is still 2 minus, right? So now we have 2 coppers, therefore each one has to have 1 charge, so it's Cu plus, just 1, because we have 2 of these. So technically we have Cu plus, and then O2 minus. So the systematic name for this is copper 1 oxide. And the common name would be cuprous oxide. Another example here we have is iron and oxygen, right? Same as the copper, we have oxygen as 2 minus, so therefore Fe has to be 2 plus. And this systematic name is iron 2 oxide, and the common name is ferrous oxide. For our final example here, so we have O2 minus, and we have Fe, and the charge here is going to be 3 plus. Why is that? So we see that here we have 3 atoms of oxygen and 2 atoms of iron. So if we multiply them, remember when I showed you before, when you multiply the charges so they're neutral, you do one side times the other side, and then the other side times the first side. So the systematic name, I didn't write here. We have it in the chart before. So we have our iron 3, which is ferric. So that would be, scrolling down, iron 3 oxide, and the common name would be ferric oxide. Now I'm going to go over the ionic compounds that contain polyatomic ions. To name an ionic compound containing polyatomic ions, name the positive ion first, followed by the negative ion, and each is a separate word. So we have our polyatomic ions table here. I am repeating that table. An example here says, name these ionic compounds, each of which contains a polyatomic ion. So we have NaNO3, right? NO3 is NO3 is right here, is our nitrate. So Na is the sodium, that will be sodium nitrate. Then we have CaCO3. The CO3 I'm trying to find it. Did I miss it? Okay, well this one here says hydrogen carbonate, HCO3, so CO3 is just carbonate. Not sure, it's not here. I don't think I missed it. So CaCO3 will be calcium carbonate. Then here we have NH4, SO3. NH4 is our ammonium, and SO3 is our sulfide. So that will be named ammonium sulfide. And our last example is NaH2PO4. So we have NaH2 and PO4. Na, sodium, H, hydrogen. PO4 is the phosphate. PO4 is right here, phosphate. So how do we write this? Sodium. How many hydrogens do we have? 2. What's another word for 2? Di. Dihydrogen phosphate. So how does this actually relate to the medical field? You might be asking yourself. If you look here, there's this table. The formulas are on the left side and what it's used for. So we have silver nitrate, which is an antibiotic. Sodium bicarbonate, it's antacid. So there's a lot of things. Chemistry is related to medical field. It's just taking this class will make you understand all that. So what is a covalent bond? I'm sure you guys took that in high school chemistry, right? Formation of a covalent bond. A covalent bond forms when electron pairs are shared between two atoms, right? We went over whose difference in electronegativity is less than 1.9. And the most common covalent bonds occur between nonmetals and metalloids, or between two nonmetals. According to the Lewis model, a pair of electrons in a covalent bond functions in two ways. The two atoms either share it or it fills the valence shell of each atom. So an example here is a hydrogen molecule, H2, right? Each hydrogen has one electron, and we know that the first shell can take a maximum of 2 electrons. So when you put two hydrogen atoms, they will share these 1 electrons to fill that most outer shell. And we know for the first shell it's 2, right? So if I redraw this, hydrogen has 1 and another hydrogen has 1. So that would become hydrogen like this. So both hydrogens, their most outer shell is filled by sharing the 2 electrons. This bond is called a single bond, and we usually represent it by a line. So this you can rewrite like H dash dash H. Nonpolar and polar covalent bonds. Nonpolar covalent bond, electrons are shared equally. Polar covalent bond, electrons are shared unequally. Sorry about the typo there. So let's look at this table now. Electronegativity less than 0.5 is nonpolar covalent. Electronegativity between 0.5 and 1.9 is polar, and greater than 1.9 is ionic. So here's an example. We have hydrogen and chlorine. Hydrogen has electronegativity of 2.1, as you can see here, and chlorine has an electronegativity of 3.0. So the difference between them will be 3.0 minus 2.1, and that is equal to 0.9. So what's that? 0.9 is between 0.5 and 1.9, therefore it's a polar covalent. Here it says classify each bond as nonpolar covalent, polar covalent, or ionic. So we have here N-H, right? So nitrogen and hydrogen. Nitrogen electronegativity is 3.0 and hydrogen is 2.1. So we'll do 3.0 minus 2.1. That is equal to 0.9. What does that mean? 0.9 is between 0.5 and 1.9, therefore it's a polar covalent. So this is polar covalent. Then we have Na and F. Sodium is 0.9, fluorine is 4.0. We take the difference, 4.0 minus 0.9, and we get 3.1. What is 3.1? 3.1 is greater than 1.9, therefore it's an ionic. Our next example is C-S. Carbon is 2.5, S 2.5, so we have the difference 2.5 minus 2.5, that gives us 0. What is 0? 0 is less than 0.5, right? So that's nonpolar covalent. Nonpolar covalent. All these are calculated by taking the difference in electronegativity. Consequence of unequal sharing of electrons in a polar covalent bond. The more electronegative atom gains a greater fraction of the shared electrons and acquires a partial negative charge. This negative charge is shown by the symbol delta minus. I couldn't find the symbol in the system, so I hand wrote the delta for you. And the less electronegative atom has a lesser fraction of the shared electrons, and that is acquires a partial positive charge, that therefore it's indicated by the symbol delta plus. This separation of charge produces a dipole, which is two poles. We commonly show the presence of a bond dipole by an arrow, with the head of the arrow near the negative end and the dipole negative end of the dipole, and the cross end of the arrow is near the positive end. So that is shown here for you. You guys see that? So it would be like that. The polarity of a covalent bond can also be shown in an electron density map. As you can see here, the electron density map of HCl, the red indicates the region of high electron density and the blue is the lower electron density. So let me go over an example. It says here, using the symbols delta plus and delta minus indicate the polarity of each polar covalent bond. Remember, the more electronegative atom of a covalent bond bears a partial negative charge, and the less electronegative atom bears partial positive charge. So our example here is CO. Carbon and oxygen. So, carbon and oxygen. Carbon has an electronegativity of 2.5 and oxygen has an electronegativity of 3.5. So how do we write this? So whatever is higher has the partially negative. So this is negative and carbon is partially positive. So how do we put the dipole? We draw the dipole as arrow going to the partially negative. Another example here, we have nitrogen and hydrogen. So nitrogen has electronegativity of 3.0, right? And hydrogen has 2.1. So the lower one is partially negative, higher one is partially the higher one is partially negative and the lower one is partially positive. And the dipole for this will go the other way. Last example here, carbon and magnesium. Carbon is 2.5, 1.2. So 1.2 is lesser, so it's partially positive. 2.5 is more, so it's partially negative, and therefore the dipole will go from lesser to higher. Drawing Lewis structures of covalent compounds, there are steps to follow. The first step is to determine the number of valence electrons in a molecule. Step number 2 is to determine the connectivity of the atoms, which atoms are bonded to each other, and connect bonded atoms by single bonds. And then we have to arrange the remaining electrons so that each atom has a complete outer shell. Sometimes we'll have double bonds and triple bonds. So double bonds is where two atoms share two pairs of electrons, and we represent the double bond by having two lines like this. And then for triple bonds, it is sharing 3 pairs of electrons, so it's shown by 3 lines. So here I can show you that in ethylene we have the double bond. Here we have the triple bond. You see how there's 3 lines? And then you obviously know your single bonds. I went over that. So let's do an example. State the number of valence electrons in each molecule and draw a Lewis structure for each. We have hydrogen peroxide. We have 2 hydrogens and 2 oxygens. So oxygen, we have 2, and it has how many electrons? Oxygen, if we look on the periodic table, oxygen has 6 outer electrons. So 2 oxygens times 6 electrons, that'll give us 12 electrons. And then for hydrogen, we have 2 hydrogen atoms times, we know hydrogen has 1 electron, that'll give us 2. So in total we have 14 valence electrons. Our next example is methanol, which is CH3OH. So carbon has 4 electrons on its most outer shell. How many we have? We have 1 carbon. Hydrogen has 1 electron on its most outer shell, and how many we have? We have 3 here and 1, so that's 4 hydrogens. And for oxygen, oxygen has 6 electrons on its most outer shell, and we only have 1 atom, and that is 6. So when we add these up, we get 14 valence electrons. Another example here is acetic acid. So we have the carbons. Carbon has 4 electrons on its most outer shell. We have 2 carbons here, so we multiply it by 2. That's 8. Hydrogen, how many hydrogens do we have here? Hydrogen has 1 electron on its most outer shell. We have 3 and 1, that's 4. 1 times 4 is 4. And then we have our oxygen. Oxygen has 6 electrons on its most outer shell. How many oxygens we have? 2. 6 times 2 is 12. And when we add these up, we'll have 24 valence electrons. Exceptions to the octet rule. Atoms of period 3 elements. We have 1 3s orbital, 3 3p orbitals, and 5 3d orbitals. It can accommodate more than 8 electrons in the valence shell. So an example here, we have the phosphate and the sulfur. You can see how we have on each line there's 2 electrons, right? So now we have a double bond here, so that means there's 4 electrons there. And the phosphate, you can see, gets all 5. And then for sulfur, here we have an electron on each bond, and the double bonds have 4 electrons. So the sulfur will get 6. So how do we name binary covalent compounds? A binary covalent compound is a binary, which means it has 2 elements, right? And it has all covalent bonds. So in naming binary covalent compounds, the first thing we do is first we name the less electronegative element, which is also written first in the formula. Then we name the more electronegative element, which is named second in the formula. We use the prefixes di, tri, tetra, and so on to show the number of atoms. We don't use mono to say that there's one, except for CO, which is carbon monoxide. So the name is then written as two words. The first is the first element, and we use the di, tri, tetra, and so on. And then the second is the second element, and we use the prefixes mono and so on. So note here, the use of prefixes is only for binary covalent compounds and should not be used to name the ionic compounds. Okay, guys? So an example here says, name these binary covalent compounds. We have NO, we have one nitrogen and one oxygen. So that's nitrogen oxide. This is also known as, side note here for you, nitric oxide. Next we have SF2, sulfur and fluorine. So that we have two F's, so that will be the di, right? So first we name S, sulfur, and then we have difluoride. Here we have N2O, so we have two nitrogen. How do we name the two nitrogens? Again, di. So di-nitrogen oxide. So what is resonance? A theory that many molecules and ions are best represented as hybrids of two or more Lewis contributing structures. Electron pairs are redistributed from one contributing structure to the next. So if I show you an example here, is the carbonate ion. We have the carbon, we know has four outer shell electrons, so the four needs to be occupied, right? So carbonate ion has one carbon and three oxygens. One of the oxygens will have a double bond with the carbon, but another oxygen can also have a double bond with the carbon, or the third oxygen can have a double bond with carbon. Therefore, a resonance means that this double bond can be interchanged between the oxygens and the carbon. So to show the pairs of valence electrons are redistributed from one contributing structure to the next, we use these curved arrows. So it just shows you that that electron is getting moved from one place to the other. So an overall representation is drawn like this. We have one bond, right? One bond followed by this dotted lines. That means that this oxygen can have the double bond, this oxygen can have the double bond, and this oxygen can have the double bond, but they can't all have the double bonds at the same time. How do we predict bond angles in covalent molecules? So the valence shell electron pair repulsion model predicts. We have an angle of 109.5 for 4 regions of electron density, and then an angle of 120 degrees for 3 regions of electron density, and 180 degrees of 2 regions of electron density. So let me show you here. For methane, we have a carbon with 4 hydrogens, right? Because we have the 4 hydrogens, it's called a tetrahedral, and it has an angle of 109.5 degrees. And then for ethylene, we have the 2 carbons that are double bonded, and then we have the 4 hydrogens. Because of the 2 carbons being double bonded, we have a trigonal planar, and therefore the angles will be 120 degrees. And then lastly, we have the carbon dioxide. You see how it's linear, so it's called a linear, and therefore it'll have the 180 degrees. how do we determine if a molecule is polar? So a molecule is polar, which means it has a dipole. Remember we went over to dipole? If it has a polar bonds and the center of its partial positive and partial negative charge do not coincide. So if a molecule has polar bonds but the center of its partial positive and negative charge coincide, the molecule is not polar. So that's when you say it's non-polar. What is a chemical reaction? So let's get into our chemical reactions. It is in a chemical change, also known as a chemical reaction, one or more reactants, which are the starting materials, react to form one or more products, which are the end materials. 4 aspects of chemical reactions that we're going to go over is how to write and balance a chemical reaction, the types of chemical reactions, mass relationship in chemical reactions, and the heat gains and losses. So how do we balance chemical equations? We can write this chemical reaction in the form of a chemical equation using chemical formulas for the reactants and products, and then we have an arrow indicating the direction this will go. We also have to show the state of each reactant. Either it's going to be gas, liquid, or solid. We'll indicate that by the symbol G, L, or S. And AQ for aqueous, which means a substance is dissolved in water. Here we have an example, propane and oxygen forming carbon dioxide and water. So you guys see how we have the G for gas, right? And then we have our arrow indicating which way the reaction will go. So this formula written, it tells us the starting material and the products, right? Which every equation must do. And it tells us the physical state of each reactant and product, but it does not tell us the amounts correctly. And in order for me to point that out to you is, we remember the law of conservation of mass, right? Atoms are neither destroyed nor created in a chemical reaction. They merely shift from one substance to another. So all of the atoms present at the start of the reaction, which is on the left side of the equation, they must still be present at the end of the reaction, which is the products on the right side of the reaction. So here we have our equation from before. C3H8 plus O2 gives us CO2 and H2O. So we have here carbon, we have 3, hydrogen, we have 8, oxygen, we have 2. And on this side, we have carbon, 1, oxygen, 2, hydrogen, 2, and then we have another oxygen here. So we actually have 3 oxygens on this side and 2 oxygens on the other side. Our hydrogens don't match, our carbons don't match. You guys see that? We have 3 carbon on the left side, 1 carbon on the right side, and we have 8 hydrogens on the left, 2 hydrogens on the right. So we need to balance this. How do we balance this? We have to multiply and make sure that each side is balanced. So I didn't do this math in advance, I'm sorry, so I'm going to do it now. So we have, if we put this trial and error, I'm sorry in advance, if we put 4 here, that'll give us 8 hydrogens and 4 oxygens. So then that will, carbon we have 1, oxygen we have 2, hydrogen we have 4 times 2 is 8, and then 4 times 1 is 4. So this will give us 1, 6, and 8. So our hydrogens match, right? Our oxygens don't, our carbons don't. So for the carbon, we have 3 on the left side, we have to get 3 on the right side. So let's do 3 here. 3 times 1 is 3. 3 times 2, we have 6 oxygens. So now we have 6 plus 4, that is equal to 10. Okay, so now if we put, for this side, we have 2 oxygens, we gotta get that to 10. So if we put 5, 5 times 2 is 10. So we'll have 10. So do they match up now? We have 3 carbons on both sides, 8 hydrogens on both sides, and 10 oxygens on both sides. So this now becomes our balanced equation. How can we predict if ions in aqueous solution will react with each other? So many ionic compounds are soluble in water. Ionic compounds always consist of both positive and negative ions. When they dissolve in water, the positive and negative ions separate from one another, and this is called the separation dissociation. So if we look at NaCl, which is our table salt, right? If we add water to this reaction, we'll have our sodium ions and chlorine ions. What happens when we mix aqueous solutions, a solution in which the solvent is water, of 2 different ionic compounds? Does the reaction take place between does a reaction take place between the ions? So the answer for this question really depends on the ion. Let's, for example, if any of the negative and positive ions come together to form a water insoluble compound, then a reaction obviously takes place and we have a precipitate. Why does it say type equation here? It's weird. So we have a precipitate that forms. This is referred to as the precipitation reaction. So let's do an example here. Suppose we prepare one solution by dissolving sodium chloride, which is NaCl, in water, and a second solution by dissolving silver nitrate, which is AgNO3, in water. So here is solution 1, solution 2. We're going to mix these 2 solutions together and see what happens. So if we mix the 2 solutions, our 4 ions, which is Na plus Cl minus Ag plus NO3 minus, these 4 ions are going to be in one place. 2 of them will react, and that 2 is the silver and the chlorine, so Ag plus and the Cl minus will react to form silver chloride. When silver chloride forms and is insoluble in water, it will be shown as a precipitate. So if we look at this picture, once we mix these 2 solutions together, we'll have this white precipitate forming in the bottom. And that is our silver chloride. So we write this reaction. We have all of our ions on the left side. We have our silver ion, nitrate ion, sodium ion, chloride ion, and those react. The silver ion and the chloride ion react to form our silver chloride, and then we have sodium ion and nitrate ion remaining. These 2 are called the spectator ions that appear unchanged on both sides of the chemical equation, and then the net ionic equation does not have these spectator ions. So if we take these out from the equation, right, we'll get our Ag plus Cl minus is going forward to form AgCl, which is the silver chloride, and we can rewrite that here. This is our net ionic equation. We have to make sure that our equation is balanced. For this example, it is. We balance them the same way we do other equations, right? I just went over an example where it's like trial and error. We have to figure out how the left side has to equal the right side. And we have to make sure that the charges balance as well. So I think it's best if I do this example for you to understand that. It says, consider the net ionic equation for the precipitation of arsenic 3 sulfide from the aqueous solution. So we have As3 plus, right? We have 2 of that. And when we look in our product, we have As2. And then for the sulfide, S2 minus, we have 3 moles of those, so S3. How do we do that? Remember, we multiply the 3 plus and the 2 minus, so we can find a common denominator, pretty much. So what are oxidation and reduction? Oxidation is the loss of electrons. Reduction is the gain of electrons. So an oxidation-reduction reaction involves the transfer of electrons from one species to another. An example of this is oxidation of zinc by copper ions. So our net ionic equation is Zn, which is solid zinc, plus our aqueous solution, which has the copper. And when we put our zinc into the copper solution, it reacts. So our copper solution is shown by the blue solution here, and the zinc is the bar that's placed into it. And once we put it into it, the blue starts fading because the copper is coating on the zinc, and the zinc bar is partially dissolving into the solution. So this is a chemical reaction taking place. So the zinc atom loses electrons to the copper ion and becomes zinc ions. So when we look at this equation, the zinc is obviously becoming oxidized, right? We're losing the zinc. And at the same time, the copper ions are gaining electrons from the zinc, so the copper ions are reduced. That's when we see the blue solution turning into the clear solution. So oxidation and reduction are not independent reactions, right? A species cannot gain electron from nowhere, nor can it lose electron to nothing. So no oxidation can occur without reduction, and vice versa. In the reaction that I went over, the copper oxidizes the copper oxidizes the zinc, and then we call this copper the oxidizing agent, right? And then the zinc reduces the copper, so we call the zinc the reducing agent. Let me go over an example here. It says, identify the substance that is oxidized, the substance that is reduced, and the oxidizing agent and the reducing agent. So here we have aluminum solid reacting with iron aqueous to form the iron solid. So this is oxidation redox reaction. So we have our aluminum solid, which is losing electrons, right? Because we go from Al3 plus, so we're losing electrons to form this. And then our iron, Fe3 plus, right, is gaining electrons. So I'm going to write that aluminum, right, loses electrons. Therefore, if you're losing an electron, that means you're oxidized. And therefore the aluminum is, because it gives the electrons to the iron, it is the reducing agent. And then the iron gains electrons, right? And therefore it is reduced. When it gains an electron, it takes the electron from the aluminum. Therefore, it is the oxidizing agent. So what are formula weights and molecular weights? Formula weight is the sum of the atomic weight of all atoms in a compound's formula expressed in an atomic mass unit, which is AMU. So formula weight can be used for both ionic and molecular compounds. Molecular weight, on the other hand, is the sum of the atomic weights of all atoms in a molecular compound expressed as atomic mass units, AMU again. So an example we have here is, what is the molecular weight of glucose, which is C6H12O6. If you look on the periodic table, carbon has a molecular weight, atomic weight of 12. Hydrogen is 1. And oxygen is 16. And these are in AMU. So we have, to get the molecular weight, we have to calculate that. So we have 6 carbons, which is 6 times 12, right? Hydrogen, we have 12 hydrogens times 1.0, and for oxygen we have 6 oxygens times 16.0. So 6 times 12 gives us 72, 12 times 1 gives us 12, and 16 times 6 gives us 96. So the molecular weight of glucose is equal to adding all these, which will be 180.0 AMU. Another example here, a molecular weight of urea. So here we have NH2, so you see how here NH2 is in parentheses, so that means we have 2. This 2 represents we have 2 of this, so that would be NH2, NH2, and then this Cl. So to calculate the molecular weight, we have 2 nitrogens, right? 1 and 2. Nitrogen is 14 AMU. That will give us 28. Then we have the hydrogen. How many hydrogens do we have? We have 2 here and 2 here, therefore we have 4 hydrogens times 1.0. That'll give us 4.0. Carbon, how many carbons do we have? We have 1 carbon times 12, so that would be 12.0. You can get all these values on the periodic table, guys. I just looked up in advance so I don't waste your time. And then the oxygen, how many oxygens do we have? We have 1 oxygen, 1 times 16.0, that will give us 16. So the molecular weight of urea is, adding all of these, if we add them, we will end up with 60.0 AMU. What is mole and how do we use it to calculate mass relationships? The mole is a useful scale-up factor for atoms and molecules. It is the formula weight of a substance expressed in grams. So the number of formula units in a mole is called Avogadro's number. And Avogadro's number is this 6.02214,199 times 10 to the 23rd power. What this means is, so if we have 6.02 times 10 to the 23rd of anything, we call it a mole. So just like 12 of anything is a dozen, 6.02 times 10 to the 23rd of anything is called a mole. A molar mass of any substance is the mass of 1 mole of the substance, is the formula weight of the substance expressed in grams per mole. So that will have a unit of grams per mole. From our previous example, right, the formula weight of glucose we calculated was 180.0 AMU. Therefore, 180 grams of glucose is 1 mole of glucose. Likewise, for the urea, we calculate to be 60.0 AMU, and therefore 1 mole of urea is 60.0 grams of urea. Okay, guys? For atoms, similarly, 1 mole is the atomic weight expressed in grams, so 12 grams of carbon is 1 mole of carbon atoms. 32.1 grams of sulfur is 1 mole of sulfur atoms, and so on. Molar mass can be used as a conversion factor, converting from grams to moles or from moles to grams. Let's do an example so you understand all that. Suppose we want to know the number of moles of water in a graduated cylinder that contains 36 grams of water. So how do we do this? First of all, if you want to weigh water in the graduated cylinder, you weigh the graduated cylinder first without the water, so you can take, when you take the measurements of water plus the graduated cylinder, you subtract the weight of the graduated cylinder in order to find your weight of the water. So in this example, we have 36.0 grams of water. So water is H2O. You guys know that, right? So we have 2 hydrogen times 1.0, and we have 1 oxygen times 16.0. These are the atomic weights from the periodic table. 2 times 1.0 gives us 2.0. 1 times 16.0 gives us 16.0. So the molar mass of water is, when we add these, 18.0. We have 18.0 grams of water in 1 mole of water. Okay, so we want to know the number of moles of water. So how do we do that? We're given 36 grams, so we have 36.0 grams of water, right? And we have to use our conversion factor, so this is our conversion factor here. 1 mole of water is 18 grams of water, so we put 1 mole of water is 18 grams of water, so that will give us our moles of water. As you see, the grams of water cancel out, so 36 divided by 18 will give us 2.00 moles of water, and that's the answer. Suppose you have a beaker that contains 0.753 moles of sodium chloride, NaCl, and you want to calculate the number of grams of sodium chloride in the beaker. So how do we do this? So our final answer needs to be grams. NaCl, sodium is, we have 1 atom of sodium times 23.0 grams. So that'll be 23.0, and then for chlorine we have 1 times 35.5, that'll give us 35.5. We have to add these, and that'll give us 58.5 grams of NaCl per 1 mole of NaCl. So the beaker contains 0.753 moles of NaCl. We use our conversion factor. Remember, the moles of NaCl needs to cancel out, so we have to flip this around. We have 58.5 grams NaCl per 1 mole of NaCl. When you do the conversion factor, remember that things need to cancel out. So the mole NaCl cancels out, and we're left with 44.1 grams of NaCl. Right? We said here our final answer needs to be in grams, so that's our final answer. Another example here. How many moles of sodium ion Na plus are in 5.60 grams of sodium sulfate, Na2SO4. So first, Na2SO4, so we need to calculate that. Na, to get our conversion factor, so Na, we have 2 NAs times 23.0, that'll give us 46.0. How many S's do we have? We have 1 times 32.1, that'll give us 32.1, and then we have the oxygen. How many oxygens do we have? We have 4 oxygen times 16.0, that'll give us 64.0. So when we add all these, we get 142.1. 142.1 grams of sodium sulfate, Na2SO4, per 1 mole of sodium sulfate. So 1 mole Na2SO4 is equal to 142.1 grams. So how many moles of sodium ions? We see that there are 2 moles, right? We see that there are 2 moles of sodium ion in 1 mole of sodium sulfate. So let me write that here. There are 2 moles Na plus in 1 mole of Na2SO4. Okay? So our first step, step 1, we have to find how many moles of Na2SO4 are in the sample. How do we do that? So we were given 5.63 grams. 5.63 grams of right, 5. 63 grams of our sodium sulfate. And our conversion factor, which we calculated, we know it's 1 mole of Na2SO4 has 142.1 grams. Remember, things need to cancel out, so our grams cancel out, and we are left with 0.0396 moles Na2SO4. Our step two is, we know that each mole of NaSO2 has 2 moles of Na+, right? I wrote that for you guys here. So our step 2 will be to take this 0.0396 moles of Na2SO4, and we'll put that conversion factor, which I stated up here, 2 moles of Na and 1 mole of Na2SO4, so 2 mole Na plus 1 mole Na2SO4. So when we do that, things need to cancel out, remember, these cancel out, and we are left with, multiply it by 2, 0.0792 moles of Na+. And that's your answer. Next, how do we calculate mass relationship in chemical reactions? We have to go over stoichiometry. Stoichiometry is the quantitative relationship between the amounts of reactants consumed and products formed in a chemical reaction as expressed by the balanced chemical equation. So remember how I did that problem where I did trial and error figuring out the left side has to equal to the right side? That values that I figured out are the stoichiometry. So in an example, we would be given either grams of compound A or moles of compound A, and we need to convert it into moles of B or grams of B, right? So let's do an example so you understand this. It says ammonia is produced on an industrial scale by the reaction of nitrogen gas with hydrogen gas. This is called the Haber process. According to this balanced equation, we have N2 gas plus 3H2 gas reacts to form ammonia. How many grams of N2 are necessary to produce 7.5 grams of NH3? So there's a few steps we need to go over. The first step is that we need to convert 7.50 grams to moles. Our second step is to convert the moles of NH3 to moles of nitrogen, N2. And then our third step will be to convert the moles of nitrogen to grams of nitrogen, because the question states how many grams of N2, so we have to end up with grams of N2. So step 1, we have to NH3, let's do it here on the side. We have 1 nitrogen times 14. Hold on. Nitrogen. So nitrogen, we have 1 times 14.0. Sorry guys, this is weird to write on. That's 1 times 14.0 is 14.0. Hydrogen, how many hydrogens do we have? 3 times 1.0, that'll give us 3.0. Total is 17.0. Okay? So we have our 7.5 grams of NH3, 7.5 grams of NH3. we'll use our conversion factor. 1 mole of NH3 has 17.0 grams of NH3. That'll give us, the grams cancel out, now we have moles. That'll give us 0.441 moles of NH3. Okay, so our step 2, we have to convert the moles here to moles NH3 to moles N2, moles of N2. So we know that in our equation here, 1 mole of nitrogen reacts to form 2 moles of ammonia, right? You see, technically there's 1 here, so we have 1 reacting to form the 2. So we will use that. We have the 0.441 mole NH3, and then we have the 1 mole of N2 gives us 2 moles of NH3. The mole of NH3 cancels, so we will have 0.221 moles of N2. And our final step, step 3, is to convert the moles of N2 into grams of N2, because the question asks how many grams. N2 is 2 times 14.0, that'll give us 28.0 grams. So 0.221 moles of N2. We'll use our conversion factor, which is 28.0 grams of N2 per 1 mole of N2. The moles will cancel out, and that'll give us our final answer, which is 6.18 grams of N2. And that's the answer. Now I'm going to go over the limiting reagent. So a limiting reagent, the reactant that is consumed and leaving an excess of another reagent or reagent unused. So the limiting reagent is whatever is used up first, and then you have leftover of something else. An example here we have, suppose 12 grams of carbon is mixed with 64 grams of oxygen, and the following reaction takes place. So we have C, carbon solid, plus O2 gas gives us carbon dioxide gas. It says which reactant is the limiting reagent and which reactant is in excess. So we use the molar mass of each reactant to calculate the number of moles of each compound present before the reaction, right? So we have, this is A, we have 12 grams of carbon, and we have 1 mole, right? We have 1 of each. 1 mole of carbon forms 12 grams. This is our conversion factor, so we get 1.0 mole of carbon. And then likewise for the oxygen, we have 64 grams, right? Given in the problem, 64 grams of O2. We have 1 mole of O2 is 32 grams of O2. Remember, each oxygen is 16. 16 times 2 is 32. And that will give us 2.0 mole of O2. So if you look at these, we have 1.0 mole of carbon, 2.0 mole of oxygen. The limiting reagent, right, is the smaller value because that will be used up first. So what is the limiting reagent for this example? The limiting reagent is the carbon and the excess is the oxygen. So this is limiting, this is excess. Part B says, how many grams of CO2 will be formed? So we have CO2. We have 1 carbon. 1 times carbon is 12.0, that gives us 12.0. We have 2 oxygen times 16.0, that'll give us 32. And when we add them, we'll have 44.0 grams of CO2. So, how many grams of CO2 will be formed? We are starting with 12 grams of carbon, and we know that 1 mole of carbon has 12 grams of carbon. We know that 1 mole of carbon dioxide had created 1 mole of 1 mole of carbon used. 1 mole of carbon here created 1 mole of CO2. And then we have this right here, so we know that 44.0 grams of CO2 per 1 mole of CO2. So when we calculate this, mole C cancels, right? Gram C cancels, mole CO2 cancels, and we're left with, so this just works out, that's the same answer. So we have 12 canceling here, so it'll be 44.0 grams of CO2. In experiments, we calculate percent yield. Percent yield is calculated by our actual yield divided by the theoretical yield times 100. In the lab experiments that we do, our actual yield is whatever we get, and then theoretical yield is whatever we calculated that we would have got. And usually the actual yield is less. So if I do this example for you, it says in an experiment forming ethanol, the theoretical yield is 50.5 grams, and the actual yield is 46.8. What is the percent yield? So how do we calculate? Percent yield is actual 46.8 grams divided by theoretical 50.5 grams, and the grams times 100%. The grams cancel out, and we are left with 92.7%. That's our yield. So we pretty much recovered 92.7%. We obviously lost some stuff there. The last thing I'm going to go over is heat of reaction. Heat of reaction in almost all chemical reactions, not only are starting materials converted to products, but heat is either given off or absorbed. And 2 simple ways to remember: exothermic is heat given off, and endothermic is heat being absorbed. I think later on in the semester we'll have more of these examples, but for now just know that exothermic gives off heat and endothermic absorbs heat. And that's the end of the 2 chapters that I just covered. If you guys have any questions, please feel free to email me. The examples I went over should help you with the Cengage materials. That's the end of this lecture. Alright guys.